Alright, it's time for another math. Easy. So we're going to discuss antiderivatives again, and I showed my previous video on what it was and also examples on it in part 1 of it. Now we're going to do part 2 of this example series, and basically before that, I just want to show the table that I showed in my earlier video on the different antiderivatives of functions here. It's similar to integrals here. Basically, if you had a function here times a constant, then the antiderivative is just going to be whatever that this antiderivative is times that constant. So, and if it's two functions added together, you just find antiderivative of both. And similarly for x, and you're gonna have something like this: 1 over x. The antiderivative is just ln x, and then this just means if you take a derivative of this, you're gonna get this on the left side. So you basically work from here to there, and then derivative of e to the x is e to the x, so it is its own antiderivative. So now let's look at some examples here. These are more trigonometric ones here. So now let's look at some examples. Let's start with example 1. Okay, so now the first example basically states find g of x, or the antiderivative of this function here, such that the derivative of g of x is equal to 4 sine x plus 2x5 minus square root x all divided by x. Well, first thing we should do here, we should just simplify this one here. So we're going to have something like g of x equal to 4 sine of x plus, we just divide this on both sides, so we're going to have 2x5 over x minus square root x over x. Remember, square root x over x is just, you could write it as 1 over 2, and then this one's going to be x of 1, and then if they're the same ones, you could subtract. And same with this one here, so we're going to get g prime of x is equal to 4 sine of x plus, this one's 2x4, because it's top minus the bottom. You can see my video on power functions in the link below in the info. Basically, now this one here, we're going to have a x 1 over 2 minus, this 1 over 2 minus 1. This is going to be negative 1 over 2. Or just simplify this one here, or 1 divided by square root x here. So that's this one goes down here. So now we have this, and now we're going to use basically what the table states, what I showed before, that if you have a function like this one, and these ones are 3 functions added together, so it's 1, 2, 3 here, and then also each one has like as a constant here. So for this one, there's a constant here, so then and then this is, if this is f of x, this is the constant c. So now we just have to find an antiderivative of each single one separately, ignore the constants, and just add them up. And from the table, you know that the derivative of negative cosine of x is equal to sine of x, so that's going to be the antiderivative of this one. So we're just going to write g of x is equal to, it's going to be 4 times negative cosine of x, because that's an antiderivative of sine of x. And then this one here is going to be plus a 2, you just take the constant out. Now this is going to be an x5 over 5 here. Because remember, you're going to have a n plus 1 divided by n plus 1, and this one in this case 4 plus 1 is 5 divided by this, because if you take the derivative of this one, it's going to be x, you're going to put the 5 down, they cancel, it's going to be x4. And now this square root one here, and this is similarly to the other one, we're going to get, this is going to be, this is just going to be x negative 1 over 2 plus 1 divided by negative 1 over 2 plus 1. This one in this case is going to be 1 over 2, and it's going to be 1 over 2 here. And this is just 1 over 2. And I just wrote it here, simplified one here, put the negative out there, and then we're going to have x 1 over 2, or square root x divided by 1 over 2. Because if you take the root of this one goes down, and these cancel, and then you just subtract 1, it's going to be the same as this one here. And also remember, you always have to add a constant here, because the derivative of the constant is 0, so it doesn't matter what it is, so you always have to add this one here. So just remember, add it, just same with integrals and then whatnot. And just to simplify this one, 2 goes on top here, put the square root sign on here, plus c. So this is the answer to the question there. Oh, actually, this is a 5 here. Okay, so now let's look at example 2 here, which basically states find f, or the antiderivative of this f of x function, if the derivative of x of f of x is equal to e to the x plus 20 divided by 1 plus x squared, and f of 0 is equal to negative 2 here. And this initial value that we're given here, this will help us to solve for the c, or the constant here, so we can solve for it. So now we could do the same thing as above here to find the antiderivative of this one for e to the x is just going to be, well, e to the x. And now this one here, we could just put the constant away. Then this is 1 divided by 1 plus x squared. If I show it above here, this one here, the derivative of tan, arctan, or inverse tan is equal to 1 over 1 plus x. So that's the antiderivative in this case. So we're just going to get 20 times tan inverse tan of x, and then now we have to add a constant. So now we could apply the initial value that we're given here, f of 0 is equal to -2, to solve for the c value here. So we just plug that in. So we're going to go f of 0 is equal to -2, then we just plug in the zeros here. E to the 0 plus 20 tan inverse tan of 0 plus c. Now e to the 0, anything to the power of 0 is defined as 1. You can see my video in the info link below that discusses power functions in this way and what this would equal. So basically we just plug this in here. We're going to have -2 is equal to 1 plus, well, this one here, the tan one here, I'll just show you what this is. Remember, it's an inverse function. So if you had something like tan y equals x, then inverse tan of x is equal to y. So it's just basically solving what this value would be. And so yes, basically what this is kind of like writing if this x is 0, we're gonna have a tan y equals 0. And if you look at the graph of tan of x, this is gonna be something like this. This is something like this here. And when x is equal to 0 in this case, I mean when y is equal to 0, or if this is tan of x, and this is 0 at x equals to 0. And in this case here, since this x1 is going to be, because we're solving for whatever the function inside of this one is, so we're kind of inversing it here. So this one's just going to be 0 here. So tan of y, or y is equal to 0 at x equals to 0. And this point is just the origin there. So now if we just plug that in, we're going to have 20 times 0 plus c. And now just solving this one, we're going to get, well, we can just put it here. Just negative 1 goes over across this side here. So we're going to get a -3 equals c. So this is the value here. And you can learn more about this tan, inverse tan, in a video link below as well. So now we just plug this in there, and that's our answer. So we're going to get f of x is equal to e to the x plus 20 inverse tan x minus 3. And this is our answer in this case. And also, if you were to graph those two functions here, in this case, this is the f of x is the blue one here, and the derivative of it is the red here. As you can see, the derivative is always positive just by looking at the function here. There's no way that it could be negative, just because this e to the x is always going to be positive, whatever value you put in, and also this x squared makes everything positive here. So then, yeah, when you graph it here, you can see how this looks in this case here, where this is always going to be increasing as the derivative is always positive, and also whenever there's a minimum or a maximum here at the derivative where the red one is, there's an inflection point here. So this inflects here, and at the minimum, in this case local minimum, there's an inflection point where it's concaving down and concaves up. So this could serve as a check for your calculations. So now let's look at a last example. Okay, so now for the last example, example 3 basically states find f of x if the second derivative is 12x squared plus x minus 4 here, and you're given two initial values. In this case, you're given the second derivative and these two initial ones, f of 0 is 4 and f of 1 is 1. So because we're going to get two constants here. So basically, to get the first, we're going to get two antiderivatives in this case. The first one is f of x in this case. And this one, we just apply the same the same antiderivative rules in the table above. So this one we're going to have equals to 12x3, add 1, and then put a 3 over it, just so because when you take derivatives, it's going to be x squared. And then plus, again, 6 is going to be x squared over 2. And minus this 4, the antiderivative is just going to be 4x. The derivative of that is just -4. And then plus a constant 1. We'll call this c1. Okay, so we have one constant there. So now we keep doing the derivative here. So now we're going to do the second time here. Well, let's just simplify this first. Yeah, this one's just going to divide all of these constants. Now it's going to be 4x cubed plus 3x squared minus 4x plus c1. So now we could take the second antiderivative to get the function f of x. So f of x is doing the same thing as in the previous examples. Is just going to be x to the 4 over 4. We have to put the 4 there. Plus 3 x to the 3 over 3, like always there. And this one's going to be just simple 4, then it's going to be x squared over 2, and then plus c1. We have to add another constant here, plus c2. Actually, I made a mistake. You don't just add the second constant. You have to add, because the derivative of a constant is you have to put the x here, just like before. So this is going to be c1x plus a second constant. So we have two constants here. Because if you add two constants added to each other, it's just going to be a constant as well. So now we have this plus c1x plus c2. So this is our function here. Now let's just simplify this a bit further just by dividing out the constants. So we're going to get f of x equals 2. Well, the 4's cancel. x4. The x3's cancel. x3. This is going to be minus 2x squared plus c1 of x plus c2. So now let's plug in what we know to solve for the two constants. So we're going to get two equations and two unknowns, c1 and c2, and we can solve for it. So f of 0 is 4. Let's plug that one in because that's easier. So f of 0 is equal to 4 is equal to, we just plug in all the zeros, plus 0 minus 0, and then plus, this one's going to be 0 plus c2. So c2 equals 4. So we have our first constant. Now we just plug in the other value, and we're going to solve for c2 here. I mean c1. So now we just put this f of 1 equals 1. So f of 1 equals 1 here. We're going to equal 2 now. Put in the ones everywhere. 1 plus 1 minus 2 times 1 plus c1 times 1, and then plus, well, 4, or just c2. So now we just simplify all this. Well, this cancels, this cancels. We're going to get 0 is equal to 1 minus 2 is equal to negative 1 plus 4 is equal to, well, plus 3. So we're going to get 3 plus c1. 0 equals 3 plus c1, and then c1 is equal to negative 3, and there's our constant. Yeah, and thus we have our function here, and that's basically our antiderivative of the antiderivative. This is going to be f of x equals 2x4 plus x to the 3 minus 2x squared, and then minus 3x, this is the constant, times x, plus 4, in this case is c1, that's c2. And there's our answer here. Well, hopefully you learn from these examples here, and well, that's all for today. Remember, you can always download these download these notes from the Dropbox link below in the info. And yeah, just like always, you can do it with all the other videos. If it doesn't work, just let me know and I'll fix it up. And yeah, hopefully learn from these examples, and you could learn a bit more about the inverse tan on the video link below as well. Well, it's all for today. Hopefully you learn, and stay tuned for another math easy solution.